So sometimes corrections, geometric corrections, have to be made to satellite imagery. This is not as big of a consideration as in aerial photography because in aerial photography, the airplane is closer to the ground, and things like the relief displacement can be a big problem. In satellite imagery, typically the satellite is high enough above the Earth that isn't a big consideration, but that does still come into play, as well as all these other considerations we have to make. So the attitude and velocity of the sensor, the panoramic distortion, the Earth's curvature, the atmospheric refraction, the relief displacement, and how the image field of view is sweeping as the imagery is being collected. So we have to correct for this, or basically return things to their proper geometric position. The way that we do this is much the same way if we take a scan of a map that we get it in this right location. We do something called georectification. And with georectification, we're trying to match ground control points to points that we can identify on the remote sensing image. The way that we do this is usually with an affine transformation. An affine transformation means that we're taking this image and we can scale it. We can make it a little bigger or a little smaller. We can also rotate it. We can turn it on an axis, or we can even shear it like we would with a deck of cards. We can slide some past the other. But the important thing here is that lines that were parallel before the affine transformation are still parallel after the affine transformation. After we do the transformation, we can measure how good our transformation was by doing a root mean square error analysis of the transformation. And we can also resample all of the pixels so that we better match each individual pixel to where it should be located in the geo-rectified image. So affine transformations, if we start with a square like this would be an affine transformation of a square where it's just been rotated. This would be an affine transformation of a square where it's been stretched out in one dimension to form a rectangle. And this would be an affine transformation of a square where it's been stretched out and it's been sheared in one direction. And the important thing, once again, to remember here is that all lines that were parallel before the transformation are still parallel to each other, like this one and this one after the transformation, or this one and this one. So these would all be examples of affine transformations. And the way that we do that is that we match the control points to known points on the image, like these four here. And then after that transformation takes place, we see how much difference there is in the actual location of these. If we're just doing an affine transformation without any sort of rubber sheeting and other localized adjustments, that's going to come out with a root mean square error, which is going to tell us what the difference in these lengths are, divided by the number of different points that we're doing this for, and then taking the square root of that. And that's our root mean square error. It gives us an overall idea of how much the entire image is going to be off after this affine transformation.